The last topic for Unit 9 is going to be area of regions bounded by polar curves. So we're going to start with one curve. This is a polar curve, r equals f of theta. The interval is from alpha to beta. Now you could say a to b, it doesn't really matter. Traditionally, a and b refer to x coordinates or possibly y coordinates. And remember, all of the points on a curve, on a polar curve, also have an xy ordered pair. So the fact that we're using Greek letters, not a big deal, but we're talking about the angles. So this angle right here would be alpha, and then beta would be this full angle here. All right. So if we think about when we started our conversation with area in Unit 6, we talked about the idea of a Riemann sum where we would take a region and we would divide it into an infinite number of rectangles. So I could have a curve like this, and here's A, here's B, and here's some function, and I could divide it into a bunch of rectangles, okay? And then we said, well, that's an approximation. How do we make an exact area? For an exact area, we have to have an infinite number of infinitely thin rectangles. So each of these rectangles, obviously I can't draw infinitely thin, but each of the rectangles, all squished together, are infinitely thin, meaning we could say the thickness of them is dx or delta x. And then the height of each rectangle is the value of the function, okay? And because a definite integral is a Riemann sum, we could find our area from this infinite Riemann sum in terms of an integral. So we do the integral from a to b of f of x dx, and that would give us our area or net area if part of the curve was negative. All right, so again, the idea was based on rectangles because in geometry, all of area is based on a rectangle. Okay, so let's apply that to what we know about polar functions. When a function is defined with a polar equation, it is the radius in terms of the angle. So we're no longer looking at xy coordinates. We are looking at a distance from the pole. So this distance, this radius value, or this radius value, or this radius, like whatever these lengths are in terms of their angles. Okay, when we do that, and if we have an infinite number of them, what we see is we have a lot of really, really, really small sectors. Okay, so with polar functions, instead of basing everything on a rectangle, we are going to base everything on a sector or a little pie slice, a very, very thin pie slice of a circle. Now, the radius of that circle is changing. So using a circle is not super exact, but it's as exact as calling these rectangles, really. So let's refresh on that. The area of a sector is equal to 1/2 r squared times theta, okay? And if you're unfamiliar with that, or if you don't remember where it came from, remember pi r squared is the total circle, but our percentage, or our fraction of the circle is whatever the central angle is over the full circle, which is 2 pi, and then we end up with r squared times theta over 2, which is the same thing as what I just wrote there, other than the 1/2 being in front. Okay, so that's where area of a circle, or area of a sector of a circle, comes from. You need to have that formula memorized, okay? That's one we should definitely know by now. All right, so what are we doing with that? That is now the thing that is going into our infinite, not a Riemann sum, but like a sector version of a Riemann sum. It's the thing that is going into the definite integral. Okay, so that would be one sector. If I want the sum of a lot of infinite sector areas added together, then my total area is going to be, and I'm gonna, 1/2 is a coefficient that's always present, kind of like pi with a solid of revolution. So usually we see that in front, doesn't have to be, but I'm gonna write this as 1/2 times the integral from alpha to beta, because it's in terms of theta, and it's not, this is where we make a common mistake. We don't just take our function and plug it in the same way we do with rectangular coordinates. It's r squared, and r squared means f of theta squared. So I'm going to write r squared first. R squared times, and then if we would ask what is the really, really tiny thickness of this sector over here, that is a very tiny change in theta, so d theta, okay? Or in other words, 1/2 times the integral from alpha to beta of f of theta squared with respect to theta. All right, there is your formula. Memorize it. Okay, do not think that area always means just the integral of the function from first point to second point, from A to B. In this case, we are not doing rectangular area, we are doing sector area. So we have a 1/2 as a coefficient. We also need to square the integrand, and you can imagine that's a really easy mistake where people forget to square, or maybe they forget the 1/2, but make sure we have both of those. All right, let's do an example. So we have a limacone 3 plus 2 cosine theta. Okay, so A, this is where A is bigger, so this is like the Cardi A shape. This is like the lima bean or kidney bean or whatever one it is. And it's a cosine with a positive, so I'm looking at something kind of like this. I'll draw it a little bit better on a graph though. So we know that our radius is starting, let's do purple. Our radius is starting at 5. Okay, we have a radius of 5. And then when cosine becomes 0, which is at pi over 2, then we're at 3. And then our smallest possible radius will be at when theta equals pi, because then I'll have a -2 here and I'll have a radius of 1. So we'll call that 1. Now it's a -1 because it's the the x coordinate is -1, but the radius is 1 because we're at pi. And then symmetry, down here at -3. Okay, and then I'm going to try and make this look kind of the way it's supposed to. Well, yeah, it's close. Try again. Maybe I'll edit out that first one. If you heard me say that, I didn't edit it out. Okay, I don't know if that's better, but we see it. We have enough. Okay, so we are looking for the area of the region inside here. Now, when we are doing polar area, not all the time, most of the time, symmetry can help you. We do need to know what values of theta are our limits for the integrals. Okay, I am going to use the fact that from 0 to pi gets us all of this top stuff. Actually, let me shade that. From 0 to pi gets us all of this. And because there is symmetry, I'm just going to take that and multiply it by 2, which is especially convenient because the integral formula has a 1/2 in front of it, so those are just going to cancel out. All right, so when I write an integral for this, I am going from theta equals 0 over here to theta equals pi. Okay, and again, I'm doing 2. Obviously, we don't have to write the 2 times 1/2, but I'm writing out everything I'm thinking here. So it is twice the integral of the pink part, which is 1/2 the integral from theta equals 0 to theta equals pi. Okay, it is not from -1 to 5. It is theta to theta, okay, so 0 to pi, of r squared, which is 3 plus 2 cosine theta squared. And then so that cancels, and then we can distribute the square. Just kidding, no we cannot. At this point, we are going to stick it into a calculator, or we are just going to stop there, or classic ... math. If this was one that we were doing by hand, we would need to expand that. I know for a fact that this is not one that we would need to do by hand because the cosine squared theta with no sine attached to it has to be done with a half angle identity. So if somebody wants to pull that out, they're welcome to do it, but I'm guessing you probably don't want to, and no, it's not going to be on the test. Okay, so that's that. I am going to stop this video and I'll make a second video where I do a couple more examples.